So I did my talk last time on graphs and graph theory, and I wanted to do it again on graphs because graphs are really nice and they're really applicable to the world around us. And so, last time I said in my previous talk about coloring graphs that when we have such as a network, such as airplane flights as we've shown here, that there is a vast amount of points there that is really confusing to parse out and see what it actually is and what we're dealing with and how much we can color it. Well, this time I'm going to be talking more about graph isomorphism, and I'll go over that a little bit. But this right here, how do I make this airplane graph of destinations and flights going in and out, and some of them go from Papua New Guinea to Australia to China to Africa and maybe go back, And so when we have that, we want to create graphs that are really isomorphic to one another, so it's more simpler for air traffic controllers, to have graphs that they can easily see and easily parse out of all that data that's shown in air traffic controls. And so, we want to start really simple. I have a nervous stick with It's just a checker in my mind, and it's a checker for you guys if you have any questions. And with this, we have a simple graph. On the left, it has 4 vertices with 3 edges, and on the right, it's 3 vertices with 3 edges. And what graph isomorphism is that every vertice, corresponds to another vertice on the second graph, and every edge corresponds to another edge on the second graph. And as we see here, we have 4 vertices on the left and 3 vertices on the right, making this not really isomorphic. And we can also do a matrix example, for example, applying the points in matrix form of what their edges correspond to the points of that graph. And so what we get out of this is an n by n matrix of how many vertices that we have. So if there's 4 vertices, for example, there's a 4 by 4 matrix, as shown on your left. And if there's 3 vertices, you get a 3 by 3 matrix, as shown on the right. And obviously, you can tell the difference. You can't really rearrange the matrix to make it really look like one another. So these are not isomorphic, and that sign.
Brandon, go back to that matrix for me. Why does that second row of the 4 by 4 have 3 ones in it?
Because when we do the columns, I didn't really list out about rows and columns, but basically you take each one of these vertexes and label them V1, V2, V3, V4, And so you say V1 connects with, so V2, V2 connects with V1, but V2 does not connect with itself, and thus you get the 0. And where V2 connects with V3 and V2 connects with V4. And that's how you get that row form.
So that second row having 3 ones in it means that's corresponding to
what it's connected to, Okay. But you really get problems with this isomorphic type of deal once you have a really big plot of dots, Maybe your computer system can't handle the amount of dots that are there on your n by n matrix, and thus your system fails. So that's a really big problem, and us mathematicians have to go and say, okay, how do I solve this problem? And so we're going to do another example, in which we have 2 graphs on the left and the right again. I'm going to call one G and one H. And they're all going to be correspond to vertices that are shown right here, And what the definition of being an isomorphic graph is that you have to have equal vertices and equal edges, just like I said, but it has to follow that you have the vertices of G going to the vertices of H, such that when you have the edges, of the points of the vertices U and V, I'm sorry, I got confused there. When you get the points of U and V that correspond to an edge there. And if and only if you take your function such that theta of u times theta of v will equal that edge, And we'll see here how that works out. So basically, I'm mapping v1 over here to 1 over here. I'm mapping V2 to 2 over here. I made it very easy for you to understand that. And V3 maps to V3, and so on and so forth. And so you get this pattern here of V1 through V5 and 1, 2, 3, 4, 5, as I laid out here. And thus you take your definition theorem of what a bijection is with a graph and get so that theta V1 times theta V3 equals edge 1, 3, right? You get this edge 1, 3 from vertice 1 and vertice 3 corresponding to this edge here. And that's getting the edge of H, this H graph here, okay? And thus it's isomorphic, right? If you do all the points of that graph, and that can get time consuming if you have a lot of points. But when you do all the points of that graph and map them together with that formula, you'll find out that it's isomorphic. And now if we pull it out right, if you like tilt your head 90 degrees, and I pull out this vertex, right, going out here, you'll see that the graph on the left is resembling the graph on the right. And thus, it's identical to it. And we call this the invariant property of a graph. So when I go back to my presentation here, right, slideshow, front side. And now we're going to see one that's not really isomorphic, right? We have the same number of vertices and edges on our graph, but like, you're saying to yourself, well, how can I get the left one looking like the right one? It looks like two different types of things out there. One's a cube and one's a pizza, right? How do I get a cube turning into a pizza, for example? And so basically, we know that there's the same number of edges and there's the same number of vertices. And then we're going to color and pick a vertice such as the top yellow one on the left and color that and say, okay, I don't want any adjacent vertices to be colored as the same one as the yellow color. And so you choose adjacent vertices and thus get the 4 vertices shown here on the left-hand graph. Whereas the right-hand graph, right, and when we do the same thing, I choose 1 point to be yellow. And when I choose that 1 point to be yellow, I choose the purple color to signify that these edges, these points of vertices cannot be used when I make adjacent edges. And then I get another point, and I plot that. And I get another point, and I plot that. And so all these vertices are now used up. And now you can see that there's a difference in which it doesn't make it isomorphic due to the adjacencies of all these yellow dots, of 4 yellow dots on the left-hand side and 3 yellow dots on the right-hand side, make these graphs not isomorphic to one another. And so there have been recent developments with this type of graph theory, and there's Sage, which you can use and type in your matrix of your graph, but again, if you have a really large one due to networking, it's going to fall apart really fast if the computer can't handle the space load. And so, but Sage can do for really simple graphs that have points designated to it. Also, there have been also time modulars in which people have used to do that as well, such as reshaping the graph, like I've shown you, for example, where I pull out the point, right, and make you tilt your head a bit, and you're like, yeah, that looks like it. And so there's been time simulations in which that has been done. Thank you.